discussing methane emissions and inventories. So, where is yours? Good luck.
So really excited to be here. My name is Harshil, and today I'm going to be presenting some work that we've been doing in collaboration with a few academic partners and a few industry partners on why methane is important and how can we build sort of a most robust strategy to impact and to have the largest impact and mitigate the most amount of methane. So I'll be this work was done with a few different collaborators that are listed below. It takes a village. And I'll get things started. So the first question, which I'm sure you're all wondering, is why? Why do we care about methane today? And why is it in a session about carbon emission and storage? And the reason is actually really simple. Methane is anywhere from, depending on who you ask, 50 to 150 times worse than carbon dioxide in its warming potential. So this plot is from a paper that Bob in the audience wrote on sort of the impact directly on the global warming potential that both carbon and methane can have if you assume business as usual. And you can see that basically, if things go as they have been for the next 20 years, you can the impact of both carbon and methane is very similar on the planet. But I want to focus on the right side of the graph. The reason that we think that methane is really important in the short term is because of its decay. So any methane emissions that you stop today will basically have a very large impact on the climate in decades instead of centuries. So you can see the CO2 will live in the atmosphere for centuries, but methane will break down in decades. So any short-term climate plans need to include methane for achieving sort of a high level of mitigation. A lot of you might be familiar with the Aliso Canyon gas leak. So this single methane leak, natural gas leak, was more than 8 million tons of CO2 equivalent in emissions. A single leak spanning days, not decades, caused more emissions than 2 million cars on the road for a year. So methane emissions can really be disastrous for the planet, and we must find ways to kind of stop them. So these are kind of the two reasons why we're thinking about this today. Methane is greenhouse gas. The second question, I'm sure you're already thinking of, why now? The funny answer to this is because there is a lot of research funding going into methane research right now. There is more than $850 million being dedicated by the US government, EPA, and DOE on basically this question: how do we most effectively mitigate methane emissions? The more serious answer is that oil and gas emissions are anywhere, again, depending on the US, for anywhere from 20 to 40% of the total methane emissions volume. So fossil fuels are a big proportion of the overall amount of methane that goes into the atmosphere. The key part why this is low-hanging fruit is that a good proportion of these emissions are actually repairable. Now, landfills, livestock, etc., the other methane sources, they're hard to stop, but oil and gas emissions are actually relatively easy to stop depending on the root cause. And there can be a variety of root causes like tanks, compressors, malfunctions, and the wellhead, or things that are simple but hard to find. So this is a key point that I'll keep coming back to. So the key idea here is that methane emissions are low-hanging fruit. So methane is potent, methane emissions are low-hanging fruit. Why have we not solved this already? And the answer is because it's not just the Aliso Canyon gas leak, right? Like, it's not just one nice source that you find and then stop. Oil and gas infrastructure is extremely spatially diffuse and can span hundreds to thousands of square miles. So it is very hard to actually find that needle in the haystack to know where to stop these emissions. So this is a picture from the Permian Basin in Texas and New Mexico. And you can just see the scale, right? Like each of these individual squares is a single well pad. And those little like kind of scars on the earth are little pipelines. So these are all potential sources of methane emissions. What I'll show now is very I've taken some artistic liberty. This is not a real survey in any way, but I'm trying to show why measuring methane is difficult. And the answer is that because of sort of the variety of root causes possible, they can kind of happen anywhere, anytime. I've kind of stylized a couple of potential sources. They can vary in size, they can vary in frequency, they can vary in duration. And I just have a little time series that shows why this is hard. And they can happen, early in the morning or late at night. So it like really is a very hard problem to solve. So the next question is like, how do we actually like find these emissions today? Like, what is the state of the art? Satellites are obviously kind of the first thing that you probably think of, go high up, cover everything pretty often. The key problem with satellites today is that the spatial resolution is not high enough to actually attribute to one of these little well pads and actually associate it to an operator. And this is a problem because if you're thinking about mitigation, the only way to stop a methane emission is to convince the operator to go fix the equipment that is causing the methane. So satellites are not quite it today. The other solution is something called a continuous monitor. So these are fixed sort of things that you can attach to oil and gas infrastructure that continuously monitors the amount of methane at the site. There are a couple of reasons why sort of this is still not ideal and this is not sort of the most widely adopted technology today. One of the big ones is it's not easy to scale, they're expensive. And the other one is that they're sometimes not great at quantifying the amount of methane. Because these emissions, like I'm showing kind of cartoonishly here, they can span hundreds of meters to kilometers, right? So if you have a single fixed sensor, it can't really actually quantify how much methane is leaking if it's spanning, a kilometer. So kind of the company that I work for, Inside Amp, are kind of, we're kind of in the middle, right? So our main technology is fixed wing airborne sort of remote sensing sensors that can detect methane and quickly survey areas. So this is kind of this middle ground for having high enough sensitivity to find a lot of emissions, but also having the scale to actually survey these large areas quickly and cost efficiently. So for the second half of the talk, this is the thesis. Measuring methane is difficult. I hope I've convinced you because both emissions and the detection technologies used to find these emissions, they both vary in space and in time. So these are like key problems that we must solve. We can't really control the emissions profile directly. So what I'll be talking about for the rest of this talk is how can we build an airborne survey that can kind of respect the variability both spatially and temporally. So the first key point I want to make that makes designing a survey strategy hard is that very rare large emissions disproportionately contribute to the total sort of volume of methane emissions. So it's all scientists in the room and engineers in the room. Imagine a fat-tailed or heavy-tailed distribution. So this is exactly that, right? Like rare events contribute most of the volume to a certain process. Here I show a plot, sort of from some work we did with the Stanford Research Group on quantifying how much of methane emissions are actually coming from these so-called super emitters, these rare events that are rare, that happen infrequently, but are very important to understand the dynamics of, to actually do any effective methane mitigation. I showed two basins here. One is the Permian Basin, like the photo I showed earlier, and another one is the Uinta Basin somewhere else in the US. I'll come back to the difference here in a bit, but I wanna sort of highlight that there is a difference in the basins, depending on where you're looking. So effective methane mitigation will require thorough accounting of these so-called super emitters. I just also want to shout out that Jordan will be giving another talk specifically about the Permian Basin, kind of going into more detail here. So I'm very excited for that. And we'll learn a lot more about the Permian in detail. The second question, which the cartoonish illustration kind of showed, but I want to quantify, is that emissions can be intermittent, right? So depending on the process or the root cause of an emission, they can last anywhere from sort of minutes to years, right? They can be very persistent, or they can be extremely short-lived. So imagine an extremely large emission that only lasts a few minutes versus a small persistent emission that lasts years. The volume for those, even if their rates are apart by 3 orders of magnitude, can still turn out to be the same just because multiply the time. So this is a key problem, and we don't really know this profile, right? Like, because we are still fully trying to understand the root causes of these emissions. So that means that we don't actually really fully know what the intermittency profile actually looks like. So you have to kind of plan your survey strategies around that key fact of methane emission dynamics. I alluded to this earlier in that plot of the super emitters, but I want to reiterate this point that different basins in the United States and kind of worldwide can have very different emission profiles. I recreate a plot here from the sort of same paper that plot was from, which shows a few different basins in the US and how much methane is being lost. That's y-axis for those different basins. And you can see that, ignore the numbers, but you can just see the difference, right? These differences are driven by different physical characteristics and operational characteristics of these basins that we'll come back to in a bit. The other point I want to also sort of the seed I want to plant is midstream infrastructure. So pipelines are actually extremely important in addition to the well pads. And we find anywhere from around 1/3 of the total emissions volumes can come from these pipelines, which is difficult to reckon with because pipelines are actually really poorly mapped. And if you don't know where you're looking, how are you actually going to find 1/3 of the emissions? So this is a key problem that we need to come back to. So this has all been kind of teeing up the main problem of sort of designing an airborne survey strategy for methane mitigation. Super emitters are rare, but form the majority of the total emissions. So this point I want to highlight as a spatial sampling point. You need to sample a lot of sites to find that one rare event that is a super emitter to actually fix it, right? So the sampling is critical, spatial sampling is critical. Emissions can be intermittent. So if they last anywhere from hours to years, and you don't know how long a given emission profile is going to last, you need to survey frequently. So this point matters because if you don't know the duration, you can only figure out the duration if you survey it frequently. Oil and gas basins have different emission profiles, as I mentioned, and then potential sources like midstream infrastructure is very spatially diffuse and very poorly mapped. And again, depending on the data source you use, you're going to get vastly different results for where an operator, a third-party source, and a technology provider think a given pipeline is. So there's some sanity that is lost in figuring out where pipelines are. And then finally, reconciling different studies, as I'm sure all of you are familiar with, across different work is actually really difficult. So taking the same data set, if you give it to 2 different research groups in the field right now, they will come up with different answers. So there's a need for basically a unified analysis protocol that can measure sort of both what the technology can see and what it cannot see very in a self-consistent way. So the final question, right, like the third part of the talk is how do we build this unbiased and accurate view of methane emissions at scale? The next few slides are basically going to be the solutions to those bullet points and the issues that I mentioned. So sampling size is critical. This plot shouldn't be a surprise to any statistician who works with rare phenomena. But what this plot is showing is that if you don't have a large enough sample, you are going to be unbiased, or you're going to be biased, and there's going to be a large variability in your derived sort of values, right? So any process that you're trying to describe, you will essentially not have the right view because you don't have a large enough sample size to actually get statistical robustness. I highlight a couple of different survey plans that our company is currently working on in a couple of understudied basins in the US that I'll kind of come back to at the end. Finally, I want to talk about how we actually deal with the intermittency part, the duration. So there's kind of three cases, right? Imagine the cartoon again, right? Like plane flying over Permian Basin. There are three cases. One is the emission is always there, it's persistent. The second case is it's never there, so it's never happening. A given site is never emitting, or it's intermittently emitted, right? So the probability of emission, you can kind of define as the probability of an active emission is the number of true detections or the number of valid covered sites. This formula seems really simple, but both the numerator and the denominator have like 80 different assumptions baked in that you really need to double check. So I'm going to call some of the most important ones out and kind of work through three cases. I'm running a little bit short on time, so I won't go into too much detail here, but find me at a coffee break. I'm going to dive into more detail. But the two big conditions that I want to call out, if these two conditions are not held, your statistical rigor is kind of impacted. One is the duration profile is stationary over small time scale. So if the way that the temporal evolution of emissions profiles is not relatively constant, you suffer a little bit. So this is not saying that emissions are a constant duration, but they're saying the duration profile, the distribution of durations is constant. We know this assumption is not fully accurate on multi-year timescales, but for smaller timescales, we've validated that this is okay. And two, you're not predicating covering a site based on coverage of another site. Like, you see an emission here, you're like, oh, hey, I saw an emission here before. If I go back, I'm going to see another emission. We've designed our surveys to not explicitly not do that, because that will basically, the probability term will become biased if you do that. Finally, we run thousands of Monte Carlo simulations, and after that, we come up with an unbiased emissions inventory with very robust uncertainty estimates. So Jordan's talk will have a lot more detail about this kind of how this actually looks like in practice. But this kind of what we have to sort of reckon with if you want to do methane emissions mitigation at scale. Finally, in my last 1 or 2 minutes, I want to highlight a case study that we are currently surveying for a DOE-funded project in the Haynesville and Anadarko Basin. We kind of built a survey plan that considered basin characteristics. We considered and sort of standardized our data sources procedure. Jordan did a lot of amazing work on that. We fully reckon with the fact that spatial midstream is critical. So we have a very spatially comprehensive sampling. So it's not just the number of sites, but it's also the amount of area you cover, and we're very, very mindful in that strategy. And then finally, the analysis part, right? So when different studies come up with different answers, how do you reconcile that? We've sort of published a couple of papers that really go into detail on how sort of a pathway to be able to do that, and coming up with a mechanism for basically having a very standardized protocol for analysis that makes it easier for other folks to kind of go in, do their own data, do the same analysis. Here I'm showing just representation for production, how much production there is in Haynesville and Anadarko as a whole. The x-axis is barrels of oil equivalent. And then the sort of inset is our survey area. So this is kind of the key plot that we have to do a lot of manual analysis for, and make sure that these distributions are well aligned to make sure that we're not biased in understanding these methane emissions. Finally, this is an ongoing project. We'll hopefully have more exciting results to share next year. We're flying a lot right now and analyzing a lot of that data. We also are collaborating with a satellite provider, GHGSat, who is also doing follow-up on the same areas to kind of build a fused multi sort of technology data set that is kind of unique and one of its kind in these two pretty understudied basins. So everyone has thought about the Permian. We're also thinking about kind of a US-wide view of methane emissions. More to come. So in summary, Methane emissions from oil and gas directly can contribute from anywhere from 0.1 to 0.2 degrees Celsius of warming over the next decades. Designing a survey is really difficult due to rare and time-varying super emitters and just the emissions profiles being very dynamic. And we described sort of this statistically robust survey strategy for an ongoing DOE project that considers all of these things to make sure that the results we get really can inform future studies of methane emissions. And with that, I'll kind of stop there and take any questions you have.
Any questions?
It's a very lucid exposition. Thank you. Very well done. One thing that has bothered me for a long time, one thing that Insight does really well is sort of mow the lawn. You go into a basin, you look at everything in the basin, which is a terrific capability. But only like maybe twice a year, if you have like a really motivated customer. Whereas if you had a continuous monitor at a much smaller number of sites, because as you said, they don't scale very well. I have wondered for a long time whether an investigation of every site gives you sort of the same statistics, weak statistics, as the investigation continuously over time for a smaller number of sites. This is what's called an ergodic hypothesis. It's a kind of peculiar part of statistical mechanics. And it's not always satisfied, for sure, it's a hypothesis. Have you looked at that kind of data or have any comments about that?
Definitely. So the ergodic hypothesis is actually like, I didn't enter into the flowchart slide, but it's critical to how we are actually able to do the airborne surveys as well, right? You have to assume stationarity for whatever process you're trying to describe. And under certain conditions, as you're mentioning, it's still a hypothesis, but it's a good enough assumption that you can kind of run with it. So that's kind of the second part. The first part, definitely. I think that the key concern, I think, with continuous monitoring systems, as you kind of know probably pretty well, is for doing a smaller site of surveys, one of the key things you want to get out is the distribution of rates, right? Like how big are the emissions? There has been a lot of progress in continuous monitoring to get those rates to be better. But recent work from Stanford, from folks in Colorado State, like all over the US, they've kind of shown that these rates can really be off by an order of magnitude on the larger end. At the lower end, they're not that biased, but at the larger end, because you're not capturing the full sort of view of the plume or the emission, you're really underestimating. And there are some providers that are able to do better than others, but as a whole, there's still sort of room to grow in that quantification estimations. However, I do think that there's a really nice sort of synergy in continuous monitoring and airborne in duration. Like the binary yes, no is phenomenal in the context of the WEC feeds that are coming online, right? So for broader context of the audience, the EPA is going to now directly charge operators for methane emissions that go above a certain threshold. There's a lot of nuance, but simply put, like the duration of emissions will matter a lot. And if you have a continuous monitor on the site, you will very quickly know when the emissions started, that you can then combine with the rates from an airborne or a satellite-based survey and really hone in on what the impact on the climate and the operator was pretty quickly. So yeah, we're hoping that the MERP DOE projects will start a new kind of revolution in combining data sets and not just kind of staying in, everyone kind of staying in their own lane. So it's an exciting time.
Just so I could follow up. So you said that the continuous monitors have trouble getting the high end of the leak rates and so on, which seems reasonable to me. There's that effect, but there's also perhaps the effect that if you only have continuous monitors at a sort of select number of sites, and I just wonder whether most of those huge emissions are happening from a relatively small subset of sites. Have you looked at that at all?
Definitely, yeah, root cause analysis and really figuring out hotspots and mitigating those for sure. It's an ongoing investigation. I mean, I think that that is definitely the future of having sort of a distributed strategy that sort of gets the super emitters continuous monitoring and then larger surveys to kind of cover everything and sort of less frequently, like you're saying.
Well, that's what.
That's the question you again. Thank you. Speakers, Harshil Kumar.
We're gonna help. I will send it to you, please. I can find it. Which the first one.